Today's episode is going to be all about insulin resistance, how it impacts your risk of disease, why insulin resistance could be driving so many chronic diseases of our lifetime, of our generation, and what lifestyle measures you can do right now to improve your metabolic health by increasing your insulin sensitivity and reducing the likelihood of insulin resistance. By the end of this podcast, you should have a good understanding, not just a general understanding, but a good understanding of the importance of sugar balance in the body. You'll also understand what insulin is and how it actually works. And it's a lot more complicated than it just being a hormone that allows sugar to go into cells, in and out, all that kind of stuff that you probably already know about. We're going to go into a lot more depth. We're going to talk about what happens to you when you become insulin resistant, i.e. resistant to that hormone, what the causes or the proposed causes of insulin resistance are, and what we can do today, all the different lifestyle measures to become more insulin sensitive. I've tried putting this into one podcast and it's going to be a lot of information, but we'll do another podcast where I'm going to talk specifically about glucose hacks that you've probably heard about, what the science behind those are, what the evidence behind that is, and supplements and all that kind of stuff. But we're going to do that in a separate podcast because I think that can sometimes cloud the really big wins that you can have from very, very simple things that don't require supplementation and don't require doing anything out of the ordinary. I think there's so much you can learn and benefit from just understanding insulin resistance as a concept and then putting into practice all the things that we're going to talk about. All right, so whilst I'm going to be talking about insulin resistance, I want you to remember the framework that I tend to use when presenting these ideas to you, and that is the science is complex, solutions are simple. The solutions that I'm going to be talking about are really, really simple. Implementation is hard. So I don't want to make this sound like this is going to be super easy. All you need to do is these things. Actually, the implementation and the consistency of eating well, of exercising, of sleeping well, etc. These are things that take most of the time. Understanding the science and understanding what the solutions are is just part of the problem. The main problem is implementation. Doctor's Kitchen. Recipes, health, lifestyle. So let's start off with, why am I even talking about insulin resistance? There is a growing consensus among the academic community that insulin resistance underpins a lot of the chronic illnesses that we see, particularly in the UK and the US, but is also spreading to other nations as well as a result of sedentary lifestyles and the explosion of processed foods, convenience foods, and a move away from our traditional lifestyles. And this will become clear as to why this might be driving insulin resistance. And when people talk about poor metabolic health, obesity, type 2 diabetes or pre-diabetes, or glucose intolerance, it's one of the core features of what drives it. And conversely, being insulin sensitive, which is where we want to get to, becoming more sensitive to this important hormone, that confers many benefits. So what is this relationship between insulin resistance and disease? Well, the metabolic consequences of insulin resistance can manifest in things that we can measure, things like hyperglycemia, hyper being high, glycemia being glucose, high glucose in the blood, hypertension, so that's raised blood pressure, dyslipidemia, this is an imbalance of the lipid profiles that we tend to measure on blood tests, visceral adiposity, again, fancy words, simply breaking it down, visceral, around the organs, adiposity, fat, or adipocytes, hyperuricemia. We've talked about uric acid on the podcast before with Dr. David Perlmutter. Uric acid is not just a feature of gout, it actually has a lot of, is a huge relationship with other metabolic issues, and being insulin resistant can increase your uric acid, uricemia in the blood, elevated inflammatory markers, and endothelial dysfunction. So the endothelia is the single layer of the lining of the blood cells, and dysfunction in that layer can lead to cardiovascular disease through the inflammatory process of atherosclerosis. And I hasten to add the word inflammatory because it is an inflammatory process. It's not just a case of how we've usually described it as a plumbing issue. You get stuff stuck, you get stuff plugged into your arteries. It's more an inflammatory process that involves the lining of the blood vessels, and a pro-thrombotic state as well. Again, related to insulin resistance, pro being pro, and thrombotic, so all the different clotting factors that can render you more at risk of things like strokes. So insulin resistance is related to all those things, and as we unpack it, you're going to learn a lot more about why it does. Hence, with all those collection of different metabolic issues, it's related to obesity, cardiovascular disease, cancers, hormonal disruption, things like PCOS, dementia. We talked about PCOS recently, and its grounding in insulin resistance, which is actually the sort of reason as to why I thought I should do a full pod on insulin resistance, because I don't think it's very well appreciated. Dementia, again, dementia has multiple different causes, one of which is metabolic issues and disturbances, again, can have its relationship with insulin resistance. And of course, the big one, type 2 diabetes. So the one fact that I want you to remember with all these different things, so we just talked about insulin resistance related to those different factors, related to those end points, those conditions, is think about it on a spectrum. So you have insulin resistance getting worse and worse and worse. Then you have these factors that you can measure in the blood, so things like impaired fasting glucose, where your fasting glucose as measured in your blood is higher than would be deemed normal. You have high uric acid level, high blood pressure, etc. And then the end point is when you get diagnosed with a disease. Insulin resistance is thought to precede the development of all these conditions like type 2 diabetes by 10 to 15 years. So by the time you actually have a diagnosis at, let's say, age 45, actually a lot of the issues that have been going array has started up to 15 years ago, probably earlier, if I'm honest. I think there's a lot of evidence to say that inflammatory changes, particularly in cardiovascular disease, can occur as early as in teenage years. But let's just say, for argument's sake, it's at least 10 to 15 years. That is a phenomenal amount of time where we haven't intervened and we haven't done anything. So if you can prevent if you can prevent the development of or the worsening of insulin resistance, and we can anticipate that, then it goes to say you can potentially anticipate and prevent a multitude of diseases down the line, which is why insulin resistance is such an important topic, and that's why we're doing a bit of a dive into it today. Okay, so what is it? What is insulin resistance? I think before we get into exactly defining insulin resistance, it's important to understand how sugar regulation works in the body. The body has a remarkable capacity to satisfy the nutritional needs for glucose while still maintaining a good stable level of glucose in the blood. It is pretty phenomenal. There is a paper that I will link to all these papers and references in the show notes, of course. But there is a paper called Just 4 Grams of Glucose. You can look it up. It's open. It's open source. Just 4 grams of glucose circulates in the average 70 kilo person. That is a ludicrously small amount to keep tightly regulated in your bloodstream. It is the equivalent of a teaspoon of sugar that is in my blood right now. As a 75-ish kilo person, there's about a teaspoon of sugar, glucose, in my blood right now that is constantly being kept at that level, maybe with a perturbation of another a gram or so, but it is so small. And considering how important glucose is as a molecule for the production of energy, for the maintenance of consciousness in your brain, it is quite amazing that your body is able to keep that very, very tight balance. I would liken it to acid-base balance. So within medicine, you have a very tightly regulated pH of your blood. between 7.35 and 7.45. Outside of those areas, you're running into trouble. There could be a metabolic reason as to why. Maybe you've ingested a particular toxin, or you have a respiratory issue whereby you are breathing really, really heavily. Perhaps you've got fluid in your lungs, or you have a chest infection, and then that will change the acid-base level in your blood. It is really, really tightly regulated, and I don't think I fully appreciated just how tightly regulated glucose is in your blood. Putting this into context, too little sugar in your blood can lead to neuroglycopenia, so that is brain neuro, glycoglucosepenia, too little, which can lead to seizure and death, which is why glucose is so important. And remember, 60% of the glucose used in a person who is like myself right now, sat sedentary, is being utilized by the brain. And then too much glucose is glucose toxicity or hyperglycemia. And this is where you have a persistent situation where you have high glycemia glucose in the blood. And that can lead to all the other things that we just talked about: blood pressure, dyslipidemia, visceral adiposity, so fat around the organs, high uric acid levels, and all the rest of it. Now, this is very important because sugar is generally maintained in a strict concentration of 4 to 8 millimoles per litre. I don't have the milligrams per deciliter conversion for anyone who's listening from the States, but there are many conversions online. 4 to 8 millimoles per litre is the general sort of range that we tend to have in the UK. It sounds like a high range, but it's actually very narrow if you compare it to the number of teaspoons that are being kept stable in your blood. Insulin has a central role in maintaining this tight sugar balance in your blood. It suppresses the release of glucose from the liver. Not a lot of people realize that your liver is tasked with a number of different things, one of which is maintaining a steady glucose state through gluconeogenesis that we'll come to in a second. Gluco being sugar, glucose, neogenesis, this is the generation of glucose from novel components. Your liver is constantly doing that. So insulin switches that, or suppresses it, attenuates it, mutes it, puts it down, and then it stimulates the removal of glucose from the blood into other cells where it can be stored. Muscle, liver, and fat are the key cells that you need to be aware of in this story of insulin resistance. And then the ultimate result of that is that insulin is regulating a stable amount that's in your blood. The aim of the game is to keep the glucose levels in your blood the same, because you don't want to have too little or too much, because there are some very, very nasty consequences of that. In addition to insulin, you have these glycogen reservoirs, and these are required to maintain a steady state of glucose in the blood. Now, as you can imagine, we are not having teaspoons of glucose in our diet all the time. We're having a massive amount more than that in anything that you eat. Is always going to be converted into glucose. And so with this in mind, we need to have stores. If you can only have a teaspoon of glucose in your blood, you have to store the sugar that we are pumping into our bodies through at meal times in various parts. Well, the main storage sites are your liver. There's about 100 grams of glycogen, which is the storage molecules that we store sugar in, glycogen. There's a conversion process for that. That's stored in the liver, and there's about 400 grams of glycogen that you find in the muscle. And you tap into these during exercise when you need to, or when you're fasted, for example. The liver can also create glucose from non-carbohydrate sources. So this is the process of gluconeogenesis that I was talking about. And it uses things that you don't really need to know about: glycerol, lactate, pyruvate, and glucogenic amino acids. A lot of people don't realize that proteins can be turned into sugar, and your liver does this via the process of gluconeogenesis. You don't need to know about the pathways, just know that it happens. So just to recap, you have a fixed amount in your blood that is highly regulated, and to maintain that regulation, we have hormones, insulin, glucagon is coming up in a minute for those of you that are trying to jump the gun, and then you have these stores that are basically like your savings accounts, and you tap into them when you need it. If you need to if you're exercising or you're fasting or you don't find food. These are all very important evolutionary mechanisms that would have been critical during periods of famine that undoubtedly we would have been affected by. But in today's environment, where we have an abundance of food, not really necessary. We don't really need these, but we have to manage them because we haven't evolved. We certainly have evolved over the last 50, 60 years when our food environment has completely changed. There are other players in glucose blood regulation, like glucagon that I mentioned. Even things like catecholamines, so these are released from your adrenal glands, cortisol, growth hormone, but our focus is going to be insulin today, because otherwise we're going to be basically just going to a huge textbook of biochemistry, and we don't really need to know that. Our focus is going to be on insulin. Okay, so now you understand about the importance of blood sugar regulation, why too much and too little is a bad thing, 4 grams of sugar in the blood, and the storage mechanisms that we have to maintain that level in the blood, and storages that we need to tap into during fasting or exercise. Crudely, insulin lowers blood glucose by shoving glucose into your cells and telling the liver to stop producing it. It's actually a lot more complicated. So, receptors on the cell surface of your target tissues, which are muscle, biggest sink for sugar, fat and liver cells, these passively transport glucose into the cell. Something called muscle glucose uptake is central to glucose metabolism, and insulin causes the translocation. This is moving this protein called GLUT4 to the surface of the cell, and then it allows glucose to go into the cell. This GLUT4 protein is very important, and you'll hear this or see this, read this in academic journals whenever you read about insulin and the receptor. But insulin is not just having an effect on this receptor, this GLUT4 receptor. In fat cells, insulin also works to suppress something called lipolysis or lipolysis. Lipo meaning fat, lysis meaning breakdown. Again, we're using ancient words here to describe this, or Latin words to describe this. Why would insulin suppress lipolysis in fat cells? Well, when you break down fat cells, you increase free fatty acids in the circulation. And the breakdown of those fatty acids are used by the liver to create glucose via gluconeogenesis. So the liver can utilize these different elements that are broken down via lipolysis for gluconeogenesis. So one of the extra actions of insulin is to stop or attenuate or mute that process of fat breakdown. That's really important. So again, you've got insulin stopping the glucose going into cells, you've got insulin stopping gluconeogenesis directly, and you've got insulin stopping gluconeogenesis indirectly by stopping or muting lipolysis. Really important. In the liver, it's reducing hepatic glucose production by also inhibiting the expression of gluconeogenic genes. So insulin is also having an impact on the proteins, the genes that are switching on and off gluconeogenesis. So in addition to all those different things, it's actually having an impact on the gene functions as well. Again, insulin also suppresses glucagon secretion from the pancreatic alpha cells. So glucagon and insulin are sort of like yin and yang in a very crude manner. And glucagon is responsible for increasing blood glucose. So that's why it's the yin and yang. We're not going to talk too much about glucagon today, but it does that. It suppresses the release of glucagon from pancreatic alpha cells. Insulin also has an impact on the central nervous system. It suppresses your appetite. So hopefully, and these are just a few things. I think that there's a bunch of other functions that insulin can do, but hopefully you get this idea that insulin isn't just a case of a lock and key mechanism where you go to a cell, opens up a lock, in goes glucose, thank you very much, and then back to the pancreas or broken down or whatever. It's doing a multitude of different things. It's got a suite of different functions at various sites of the body, including fat cells, liver cells, muscle cells, in the central nervous system, that all lead to a nice, stable level of glucose in the bloodstream. All right? So when you're resistant to this hormone, you can understand that a plethora of things can go awry. Let's talk about the biology of insulin resistance now. So we know where insulin is sort of working in these different target cells of glucose disposal, liver, muscle, and fat. We know it's changing genes. We know it's changing your appetite. We know it's inhibiting another hormone that is responsible for doing the polar opposite, i.e. increasing glucose. But to put it bluntly, we know what happens, but we don't fully understand why it happens. Insulin resistance, just the definition of it, is a condition in which the body cells become less responsive to the hormone insulin. So when cells become insulin resistant, they're less able to take glucose up from the bloodstream. That can lead to high blood sugar levels, and there's high amounts of this sugar in the blood over time is not a good thing. I just want to double click on the word over time, because since everyone is using continuous glucose monitors or finger pricks to measure their glucose responses to foods, which I think overall is a good thing. I think it's a behavior change tool. I've certainly learned a lot of insights from the types of whole grains and carbohydrates that work best for me. But it's really the persistence of high sugar levels over time that is the feature that we want to avoid, rather than the short bursts of increases in glucose. Your glucose level should go up after you have a meal, but it's where it goes too high and for a long period of time, that's when there are issues. And so rather than trying to flatline your glucose the entire time, which is quite abnormal because your body is used to having changes in your blood glucose, but we have these mechanisms to maintain an overall state of balance. That's really what I want you to focus on. It's more so the maintenance of these mechanisms that are in place, rather than a game where you just want to try and flatline as much as possible, because that's not the aim of the game that we're trying to play here. Okay. Insulin resistance is categorized by impaired insulin signaling and the reduced sensitivity of those target tissues to insulin, the hormone itself. So let me make an analogy that makes it easier. So caffeine. If I have half a cup of coffee and I've never had coffee before, and let's say I have a normal sensitivity to caffeine, I'm going to feel a great buzz. I'm going to feel like I can do 1,000,001 tasks. I'm going to have a really good productive morning for the next 2-3 hours, or however long that caffeine is going to stay in my system for. If I get into the habit of having 1, then 2, then 3, then 4 cups of coffee over time, my tolerance of the caffeine is going to wane. And I'm going to need ever increasing amounts of the same dose of caffeine to have the same desired effects of me being more productive and me having the sort of cognitive energy to do my task for the same period of time. This is an example of how we become tolerant to the effects of a particular substance. And you can imagine in that same example of caffeine, if I'm having lots more caffeine, it's not just having an impact on my brain, it's also having an impact on my digestive system, my catecholamines, my adrenals. I might become jittery, I might become anxious. It might have an impact on my sleep. So there are all these other effects that could get arrayed just because I need an ever-increasing dose of the same substance, caffeine, to have the same desired effect. That crude analogy is kind of like what's happening in insulin, with insulin and blood sugar. You need ever-increasing amounts of insulin to improve your blood sugar balance. However, because insulin has all these other effects, it's an anabolic hormone, it has impacts on your central nervous system, it has impacts on your fats. These are things that can lead to other issues going wrong, which overall leads to metabolic disturbances that we've described at the top of this pod. So that kind of crude analogy is something that I want you to understand. We're going to talk about the main underlying mechanisms for insulin resistance, but like I said, just hasten to say this is not fully understood. The main mechanisms are, like I said, GLUT4, insulin signaling, fat in the liver and muscle, and inflammation, which invariably leads to mitochondrial dysfunction. This is going to get a little bit technical, so just a forewarning, for the next couple of minutes, don't worry if you don't get everything. Sometimes it just takes a little getting used to, and it's hard to imagine if you don't have the diagrams in front of you. So GLUT4, like we mentioned before, is a protein responsible for transporting glucose from the bloodstream into the muscle cells. And insulin normally helps move this GLUT4 receptor to the surface of the muscle cells, allowing glucose to enter. But in insulin resistance, this movement of GLUT4 is hindered. So it's not doing the heavy lifting job of moving this to the cell membrane so glucose can enter. Interestingly, there are other ways to stimulate GLUT4, the GLUT4 protein coming to the cell membrane, even in the presence of insulin resistance. And this will come on to something that we're going to talk about later when it comes to the things and the management techniques that we can use to mitigate against insulin resistance. Exercise and conditions of low oxygen, also known as hypoxia, so that's hypo being low, oxia being oxygen, that can activate a protein that we've talked about on the podcast before called AMP activated protein kinase, also known as AMPK. And this can help with GLUT4 movement to the cell membrane to facilitate glucose transport. And remember this because it's going to be important when we come to talk about treatments and why exercise is so important, and the doses of exercise as well. So even in the presence of insulin resistance, you can move this GLUT4 protein, but insulin resistance leads to issues with moving this, and hence why more glucose is left swimming in the bloodstream rather than in the cells where it should be. Insulin signaling, that's the other thing that can go wrong in insulin resistance. So in skeletal muscle, there are problems with the signaling pathway itself, and this includes issues with activities of specific proteins called IRTK, RS1, PI3K, AKT. You don't need to know about these specific proteins, but studies have shown that these proteins may not work properly in insulin-resistant skeletal muscle, leading to reduced insulin effectiveness. The only reason why I mention these proteins is because when we talk about the causes of insulin resistance, one of those is genetics. And unfortunately, there are a few single nucleotide polymorphisms that render these proteins less effective than they should be, and that can affect certain people from different backgrounds, and a cluster of these genes that can affect those different proteins involved in insulin signaling can lead to issues with a lower dose of poor lifestyle. So me, coming from an Indian background, I have less of a threshold to tolerate insulin resistance, probably a large part due to my genes, and that's just the fact of the matter. So that's the only reason why I mention it, insulin signaling with those different proteins. Those proteins can be slightly less functioning in certain people based on your genetics, but otherwise you don't really need to know too much about insulin signaling, although that is one of the key reasons why insulin resistance goes away. Third, fat in the liver and muscle. So what we've learned about the reason why fat, essentially, when you think about fat in the muscle and the liver, I want you to think of two slightly odd things. So foie gras, which is a horrific, inhumane process whereby goose or duck are force-fed using a gavage, a very high-calorie, high-fat diet to increase the production of fat in the liver. So they're overfed a very high amount of energy, and this causes fat in the liver. They're essentially becoming insulin resistant. and steak, but not just a lean steak, a marbled steak, so something like a ribeye. That marbling in between the muscle fibers, that's essentially what is going wrong at the very later stages of insulin resistance. And it's this fat in the liver and in the muscle. First it goes in the muscle, or the general sort of hypothesis is you get insulin resistant, that leads to fat in the muscle, which leads to fat in the liver, which leads to all these other issues further down the line. It doesn't necessarily need to be in that order, but that's generally accepted. That's probably what's going on. The reason why we know a lot about this issue with fat in the different target tissues is from a condition called lipodystrophy. So lipodystrophy, there is a significant reduction in fat cells in the body's fat tissue, which leads to high amounts of triglycerides in the blood. And then what happens is you get fat accumulation in other cells like the liver, or other organs, I should say, like the liver and the muscle. And that leads to severe insulin resistance. So because you've got nowhere to put your fat other than, and you can't keep the fat in the blood, other than the liver and muscles, this is where you get fat accumulation in the muscles. And what we know a lot about insulin resistance comes from studying patients who have this unfortunate condition. Normally what happens is that after a meal, when you have an influx of fatty acids from the food that you eat, your fat tissue acts as a buffer to store these fatty acids. But in lipodystrophy, the reduced fat tissue can't handle this influx of fatty acids. And as a result, these fatty acids are basically delivered to the metabolic tissues, the metabolic active tissues like liver and skeletal muscle, which impairs insulin signaling and causes that insulin resistance. So this is one of the reasons why we know a lot about insulin resistance being associated with fat in the muscle and fat in the liver. Other studies have shown us that manipulating certain proteins involved in lipid metabolism and fat cell function can also lead to insulin resistance. So using these studies collectively to demonstrate that where there is excess fat accumulation in the liver and muscle, it can contribute to insulin resistance. Lipodystrophy is a really, really good example and important condition to render some insights around that. Okay, from fat to inflammation, although very much linked, right? Researchers who are actively trying to look at chronic inflammation in obesity, insulin-resistant people are basically finding out a lot about how everything is inextricably linked, right? So when a little primer on inflammation, when your body experiences chronic inflammation, and we're not talking about the macro picture of chronic inflammation, we're really talking about it at a cellular level, there is a prolonged inflammatory response. So your inflammatory response is very much part of your immune system. It's how we fight off pathogenic bacteria or microbes, viruses. It's happening throughout the body. But where there is a prolonged response, for whatever reason, maybe it's obesity related, maybe it's malfunction of your immune system, whatever it might be, there are changes in the production of certain chemicals called cytokines. These are the sort of foot soldiers of your inflammatory response. And what that leads to is activation of signaling pathways related to inflammation as well. So it's almost like it's a compounding effect. It's like we're gonna respond to some inflammation. We're gonna send these guys out, and those guys are gonna shout at some more guys over there, and everyone's gonna come. So you're gonna get a bigger and bigger army. So you have this sort of like chain reaction of inflammation. So when we examine obese people, so people who are overweight, and we look specifically at their fat cells, also called adipocytes. They recruit macrophages, which are other elements of your immune system related to your total immune response. And these macrophages further recruit inflammatory cytokines like TNF-alpha. And when that happens, and you have all these different cytokines and they're all sort of in the mix, it impairs insulin signaling in the cells, in particular in the liver, and that leads to insulin resistance and an increased expression of these cytokines that are happening in fat cells and other parts of the body. So with this model of inflammation, you can see how it's a compounding effect rather than the direct effect. The direct effect might be related to obesity or certain genes that are turned on. Interestingly, what researchers have demonstrated is that you can create inflammation in some of the proteins in your fat cells independent of excess body weight as well. So there is an argument to say that you don't have to be overweight to experience the same issues with insulin resistance, and that's certainly something that we see clinically as well. You can be a thin person, healthy looking habitus, and still have insulin resistance. So it's not all obesity related. However, obesity is definitely a trigger that can compound the issue. It is more likely to be associated with that as well, which is why one of the features that we use to diagnose metabolic syndrome that we're going to get into in a second is waist to hip ratio. Whilst chronic inflammation can worsen insulin resistance, it's not generally accepted to be the primary target for addressing insulin resistance in things like type 2 diabetes. Although I think if you were to improve inflammation, whether it be through diet or exercise, you can get to the root cause of, or you can definitely get to improvements in metabolic health. But I think what people in the research field would argue is that it's via a different mechanism. Who knows? You can't really talk about inflammation without mentioning mitochondria. So again, another one of these reasons, the biology of insulin resistance is mitochondrial malfunction and oxidative stress. They're inextricably linked to inflammation. Just a quick primer on mitochondria. These organelles that live in your cells, they're essential for homeostasis, and it's a fancy word for balance, energy production, signaling, and dysfunction of your mitochondria can lead to things like type 2 diabetes, aging, degeneration of your brain cells. And what's very interesting about mitochondria is that their genetic makeup is actually separate to those of humans. They're literally living bacteria inside of us that provide metabolites and energy. We have this symbiotic with remnant DNA of bacteria that we've evolved with. Studies show that reduced mitochondrial function in healthy, young, lean, insulin-resistant people is accompanied by increasing intracellular lipid concentration. What does that mean? It's basically when you have dysfunctioning mitochondria, what this leads to is an increase in the fat accumulation in the muscle cells or in the liver cells, wherever you find mitochondria. And this is problematic, as we know, because fat in the skeletal muscle and the muscle cells and liver cells can further exacerbate insulin resistance. The reason why is because mitochondria use fat for energy production, and reduced mitochondrial function is associated with that fat going elsewhere and into the cells themselves. So overall, the big takeaway is mitochondrial function and inflammation reduces the functionality of insulin in fat cells, muscle cells, and ultimately can lead to impaired glucose delivery to cells. So this is a very broad overview of the biology of insulin resistance. It's related to signaling, it's related to GLUT4 protein malfunctioning, obesity, inflammation, fat in the liver and muscle cells, and potentially mitochondrial dysfunction as well. Okay, so now we know what insulin does, the context of insulin in overall sugar balance, the biology of insulin resistance, what might be going wrong. How do we measure it? How do you figure out whether you have mild insulin resistance, a lot of insulin resistance, if you're at risk of insulin resistance? Well, this is actually part of the problem. There isn't a generally accepted and accessible test for insulin resistance. Clinically, we use metabolic consequences as markers to see whether you are likely to have insulin resistance. So when we diagnose metabolic syndrome, we're looking at impaired glucose tolerance tests. We're looking at obesity that we measure through various means. We used to use BMI. We're moving more towards a very quick tool called waist to hip ratio that you can do at home. We look at your lipid profile, in particular the ratio of HDL to triglycerides, which you can get on most lipid panels, and the presence of high blood pressure as well, and the presence of elevated triglycerides. So in the UK, we're looking at a waist circumference of over 102 centimeters for men, or over 88 centimeters for women. Or if you want to look specifically at the waist-hip ratio, you want it to be 0.85 or less for women and 0.9 or less for men. To do your waist-hip ratio, it's very simple. I would go on YouTube and look at the methodology, because you want to do it in between the bottom of your rib and the top of the iliac crest. The midpoint between there is where you do one measurement, and then you do the other measurement at the largest point around your buttocks, essentially. So, and you want to make sure that the waist-to-hip ratio is sub those levels. Very, very simple test to do, but again, full of inaccuracies, and that alone is not enough to tell whether you're insulin resistant or insulin sensitive or not. It's all a combination of all these different markers, all these different investigations that we have that would enable a clinician to essentially pull up a red flag or an amber flag as to whether you are heading in the wrong metabolic direction. But it is definitely part of the problem, because as we're going to the actual gold standard of measuring insulin resistance, it's very difficult. Raised triglycerides, so over 1.7 millimoles per liter. Those are things that we want to be careful of. Reduced HDL cholesterol. So HDL is high density lipoproteins. These are taxis that ferry cholesterol around your body. It's not a new type of cholesterol. It's not a different type of cholesterol. HDL cholesterol is the type of protein that ferries the same cholesterol that everyone has around the body back to the liver, where it can be reprocessed. So we want to make sure that we've got higher amounts of this HDL cholesterol in the context of low triglycerides as well. Raised blood pressure, so we want to be looking at no more than 130 over 85. Those are the cutoffs for the UK, although there is a trend towards less is better, obviously not too low. And then fasting plasma glucose. This, I think, even though in the context of all those different test is important, it's quite a late stage indicator of insulin resistance. So you really want to be looking at other markers of insulin resistance rather than just an oral glucose tolerance test or just a fasting plasma glucose, because as we know, insulin resistance precedes any issues with diabetes by up to 10 to 15 years. So this is why we want to get on top of insulin resistance. In research, the gold standard is something called the euglycemic clamp, also known as the hyperinsulinemic clamp. It's a research technique with limited clinical applicability. Euglycemic being eu, normal or good, glycemic, as you know now, glucose in the blood, or hyperinsulinemic. This points to, it's also known as this points to the method used in the technique, where you basically pump a high amount of exogenous, so outside of the body, insulin into the body to switch off the glucose production in the liver. So you're just relying on the glucose that one is delivering to the body. I'll explain the technique. So picture insulin being infused into one vein in a person who's lying on a couch. And the idea is to reach a constant level of insulin in the blood. And since insulin is being pumped into this person, what's going to happen? It's going to plummet your glucose. So at the same time, you also have to have another infusion of glucose. And you vary the rate of that glucose infusion to reach euglycemia. Euglycemia being a normal level of glucose in the blood. And the way we measure that is in another cannula that we put into the back of the hand. We'll be taking measurements of the blood glucose level to make sure that we're getting it to a stable level. at the point whereby you are simultaneously giving glucose infused at a varying rate until it stabilizes the sugar level to a normal level, because you've got a constant level of insulin also going in, at that point, that equals the amount that is being taken up by the body's tissues, which is a direct measure of how sensitive those tissues are to insulin. The more glucose that needs to be infused to keep that steady state of euglycemia, the more is being taken up by the body, which means that the tissue is more sensitive to insulin. So how do I explain this? The more insulin is driving glucose into your target cells, the lower your blood glucose is going to be. So if you have to infuse more glucose to maintain a steady state, that means the insulin is doing a good job, and you're sensitive to the insulin that is being pumped into your body at a steady state. It is a research technique. It is not something that we use in clinical environments, but it is very useful when it comes to the research side of things. There are a bunch of issues with this technique, however. It takes a few hours to do. It's relatively expensive, even for research standards. And across the literature, there are varying rates of the insulin infusions that we use. So some people use 40 mils, some people use 120 mils per hour. Glucose infusions are different. They're varying ways in which you can measure the sensitivity of insulin sensitivity as well. They use something called glucose disposal rate, and that's often expressed as a function of body weight, which makes it very hard to compare across individual studies. If you're just doing it by weight, then how do you categorize one group of patients that are obese versus lean? It can get very, very complicated. I don't think anyone's going to be doing a euglycemic clamp anytime soon in clinic. So there are some surrogate markers of insulin resistance that you can do in clinic. Only requires a single blood draw, relatively inexpensive to do, not 100% accurate, but they are useful. So something called the HOMA-IR, that's Homeostatic Model Assessment of Insulin Resistance, HOMA-IR. It's a mathematical calculation used to estimate, and I hasten to use the word estimate, insulin resistance based on fasting glucose and fasting insulin levels that you can have measured. It's a simple formula. You times those two together over 22.5. Values greater than 2.5 are suggestive of insulin resistance. Over 5.5 or over 6 is very sensitive to insulin resistance. But you'd have to really be pushing those values to get to that number. And by that time, it's more than likely that you have all the symptoms or all the diagnoses that are related to insulin resistance. So the value of HOMA-IR I don't think is proven out. There are a few others. There's QuickEye. These are all mathematical equations that use single blood draws to estimate to estimate insulin resistance. There are a couple of studies that have compared these surrogate markers of insulin resistance to euglycemic clamps with okay sensitivity and specificity. I think overall there are going to be other markers that we should be looking at to estimate insulin resistance. There are also things called insulin resistance indexes like Matsuda, the gut index, the Macaulay index. These are beyond the scope of today's discussion. We're not really going to go into the pros and cons of those, but there are some markers that can point you in the direction of whether you are insulin resistant or not. I honestly go for the metabolic markers that we discussed earlier, so things like blood pressure, triglycerides, the triglyceride HDL-C ratio, blood pressure, fasting glucose. The more accessible tests that I believe most people would be able to get hold of would be a fasting glucose, although like I explained, it's quite a late measure. We want to be looking at no more than 3.9 to 5.5 millimoles per liter. For the Americans, you can use a calculator to change that. I believe it's 70 to around 99 milligrams per deciliter. Those can those can indicate impaired insulin function and insulin resistance, but again, it's a very late stage in my opinion. There is a blood test called fasting insulin where you actually measure fasting insulin levels. So it's typically done overnight. You fast overnight and then you do it first thing in the morning. But this is very hard to interpret. The range of it is very wide. And we usually reserve this kind of test for diagnosing things like insulinomas, which are tumors of the pancreatic gland where you have very, very high amounts of insulin. And you're really looking for a cause as to why someone is presenting with very, very low levels of glucose and other endocrine disorders. So that's the clinical application of that test. I personally don't think it has much use in clinical medicine, apart from perhaps being used to calculate HOMA-IR. There's HbA1c, which again I think is a very late stage. So by the time you see changes in hemoglobin A1c, it's quite late. We haven't anticipated that insulin resistant journey until you're literally seeing changes in your blood glucose levels over time. But that is a general sort of marker that we use to average out your glucose control over the preceding 3 months. Glucose tolerance tests, many people have probably already done them. This is where you ingest a certain amount of glucose in the form of a drink, something around 75 grams, and then you at regular intervals test your glucose levels to look at the response. Abnormal results that indicate high blood glucose levels after 2 hours, suggesting delayed clearance, can indicate insulin resistance, but again I think that's quite a late sign. And C-peptide, this is a byproduct of insulin production. Measuring C-peptide levels can maybe help you evaluate your insulin resistance by looking at it as a surrogate marker of how much insulin you are producing and therefore breaking down. But again, I don't think any of these are particularly useful for the individual. So you're getting a picture, hopefully, that it is really hard to figure out your level or your degree of insulin resistance. And it's more a case of, well, let's do all the things that we can do today to ensure that we are as insulin sensitive as possible. Do glucose monitors have an impact on changing one's behaviors to maintain insulin sensitivity? I don't think we have long enough studies to demonstrate that, but my anecdotal opinion is that probably would be useful as a tool for certain people who love learning a bit more about their analytics. I personally think it's useful, but hey, what do I know? The other thing I want to make really clear is if all of those tests are negative, so let's say you do your all glucose tolerance test, you do your HbA1c, you do your triglycerides, you do your HDL-C, you do all these different tests, and they're all negative, that does not mean you have a clean bill of health. And I think this is something that we get very, very wrong in medicine. We assume incorrectly that if the tests are negative, if everything is within range, that's fine. You carry on, do what you do, you're fine. And then we intervene very, very late. And along that journey of 10 to 15 years where someone is insulin resistant and their body is so adaptable. Our bodies are so adaptable. If you think about it from the perspective of smoking, someone has to smoke for decades daily before they get a chronic pulmonary disorder, or they have cardiovascular disease, or they have a stroke. That isn't to say that up to that point, that was first 20 years when they were smoking, or however long it was, that they were healthy. No, it is exactly what we're doing with things like insulin resistance. We are intervening only at a very, very late stage, whereby you have the investigations that demonstrate changes in glucose maintenance, and that for me is, it's right at the end, because your body is so adaptable and has this wonderful mechanism of maintaining balance. So that's definitely something I want to make really, really clear. You get your investigations, great, but it doesn't mean that you have a clean bill of health. There are some imaging studies that I think could be useful for people, where and how early they can demonstrate insulin resistance is still up for question, I would say. So the ones that I'm always asked about include MRIs or CT scans looking at visceral adipose tissue. Ideally, you want that to be as low as possible. Higher amounts of visceral fat are commonly associated with insulin resistance, so you want to make sure that's very low. Abdominal obesity, so larger waist circumference, but you can very easily do that with a waist-hip ratio. But you can also do it on imaging as well if you prefer to have it on imaging, so you can have before afters. That's definitely something that could be, again, a behavioral change tool and give you sort of a range of as to where you are. And then DEXAs as well. So DEXAs are relatively cheap and accessible. I think you can get one for about £150 now, relatively often as well. It will give you an indication of your total body fat percentage, particularly in the central region as well. That can be linked to insulin resistance. So those are two things that you could do, or a simple waist to hip ratio that you keep an eye on, I think is useful. So a combination of all those different investigations. You've got clinical evaluation that you can get done by your doctor. You can have all those different blood tests. You can have the imaging. I think that's nice to have. These will give you some sort of inkling as to where you are on the range of insulin resistance. As you can tell, this, I think, is one of the problems that we have with insulin resistance, that we don't really know how to measure it. And I think once we find a reliable test that's easy, quick, sensitive and specific, I think it would be a real game changer for a lot of people. So let's recap before we go into some of the causes and what we can do. We know what insulin is. We know about sugar balance in the body. We know about the mechanisms of insulin resistance. We know the issues around measuring it and what the ideal scenario is with measuring it in the research lab. What are the causes? What are the sort of driving factors behind insulin resistance? So I've alluded to a couple of them already, but it's going to be a combination of genes, high sugar diet, environmental pollutants, not enough lean muscle or poor muscle health, I should say, excess fats in the blood, and also poor sleep as well. These all will lead to fat in the muscle, fat in the liver, inflammation, mitochondrial dysfunction. Also, insulin resistance can be independent of inflammation if there's fats in the liver and cell. But all those things, those catalogue of errors, those catalogue of calamities, these all coalesce to create metabolic disturbances, the driving factor being insulin resistance. I'm going to summarize those causes very quickly, and then we'll go into some of them in a bit more depth. So some people may be more genetically predisposed to insulin resistance, which can be passed down through generations. Genes, big issue, can't really do much about it. So I'm going to talk a little bit about the genes, but we're going to move swiftly on to things that you can do. Poor muscle health, a surrogate for lack of exercise, big topic. We're going to talk about that. I think that's going to be the focus of what one can do with mitigating its insulin resistance. There's lifestyle factors, things like diet and stress that can contribute to insulin resistance. Things like high processed food, sugar, saturated fats. Those can all lead to inflammation, oxidative stress, impaired insulin signaling, fat in the muscle and liver. Gut microbiome. Emerging research looking at the gut microbiome. Our good friend, the gut microbiome, is involved in everything. As you know, it's the collection of microorganisms that live mainly in the large intestine, they may play a role in insulin resistance. There's certain types of bacteria, Firmicutes and Bacteroides, these are associated with insulin resistance. These bacteria can produce different types of endotoxins. We'll talk a little bit about that and why that might be causing or driving insulin resistance. Similarly, there are some other bacteria that could be beneficial and prevent via maybe indirect mechanisms insulin resistance. Environmental toxins, difficult topic to talk about, but very important. There are exposure to certain environmental toxins, persistent organic pollutants that can render us more insulin resistant, and I think that's why we've seen the changes in what's allowed in our cookware, in our reusable plastics, BPA being the one that's been taken out, but there are other types of similar materials, even ones that are labeled as BPA free, that are just as damaging. And then poor sleep quality and quantity can disrupt your body's hormone balance, including insulin, and studies have shown that sleep deprivation can reduce insulin sensitivity as well. Okay, let's talk about genes real quickly. I don't want to belittle the strong environmental influences and lifestyle changes that one can make over the fact that, yes, there are genes that predispose to insulin resistance, but it is important to recognize that insulin resistance does have a strong heritable component. Genetic analysis has been a really powerful tool to determine what confers metabolic risk and contributes ultimately to things like type 2 diabetes, dementia, and all the other things. And I also want to hasten to add that it's not like it's one particular gene or even set of genes that are responsible for insulin resistance. As you know by now, insulin resistance is complex, multifactorial. So genetic mutations that render us more susceptible to fat deposition or obesity or mitochondrial dysfunction, those are going to play a role in individuals' own risk of insulin resistance. So when you have a test or a genomic test or whatever, and they say, you're at risk of insulin resistance, they're really looking at a cluster of different genes that can increase the risk of insulin resistance by looking at your propensity to put on fat in cells, or increasing the likelihood of insulin signaling issues, those sorts of things. The ones, there's so many different genes that could be tested and could be involved in insulin resistance. There's insulin receptor substrate 1, IRS1. There's peroxisome proliferator activator receptor gamma, PPAR gamma. There's adiponectin. I think that's an important one. That's a gene that encodes adiponectin, which is a hormone secreted by adipocytes, so your fat cells. It's a very well-known homeostatic factor, so balancing factor for regulating glucose levels, lipid metabolism, insulin sensitivity. And so when you have variations in that ADIPOQ gene, the adiponectin gene, that can be associated with insulin resistance and metabolic disorders. So, and there's a whole long list of all these different genes that potentially have a role in insulin resistance. Too many to go into this. Look, testing for these genetic SNPs, single nucleotide polymorphisms, definitely provides an individual with more information about potential risk factors. But I don't think it determines the development of insulin resistance with certainty at all. And I think there is a lot we can do within the realm of our lifestyle. And that brings me on very nicely to exercise, which we should really call muscle health. Many people believe, in the research community, believe that insulin resistance begins in muscle tissue with immune and inflammation-related changes that render the muscle tissue more likely to have fat in it, more likely to have insulin signaling issues within it, more likely to have issues with the ability of the GLUT4 protein to move to the cell membrane and bring glucose in. And also when you look at the amount that muscle contributes to glucose disposal from the blood, around 70 to 80%. You remember you have that big storage component of glycogen, which is around 400 grams. It's a huge area of where things can go wrong and also where things can go right. And so when we're talking about the things that I want you to understand about muscle and glucose health or insulin sensitivity, it's about a few things. If there's anything that you remember from this section on muscle health, it's these three things. It's about quantity of muscle, i.e. having good amounts of lean muscle, quality of that muscle, so the receptors in the muscles do their jobs effectively, and leanness, so that's the low fat amount in the muscle fibers. No point having loads of muscle and it being full of fat. It's about leanness, quality, and the amount of that muscle as well. When you have impaired muscle uptake of glucose, what happens is it goes to the liver, and when it goes to the liver, what can happen is de novo lipogenesis. That's DNL. So you have these circulating free acids that further contribute to fat being created and the production of inflammatory markers as a result of the muscle not being able to do its job. So if the muscle can't bring on the glucose, it will go back to the liver, and then you have a catalogue of other things that can go wrong, including DNL, which is de novo lipogenesis. The reason why we know this is because a whole collection of studies looking at mice and also humans where they measure glycogen synthesis. So that's the creation of glycogen storage in the liver and the muscle. When there's not enough muscle, you have this synthesis, this storage capability of glycogen being impaired, and that fat in the muscle is a big blocker of the reduced uptake of glucose. So that's one very, very important thing to recognize when it comes to one of the driving factors behind insulin resistance, poor muscle health. We're going to go back to muscle in a little bit when we talk about the things that you can do in terms of exercise, protocols, all that kind of stuff. But the muscle health, quantity, quality, leanness, these are things that you should definitely be aware of. And perhaps then looking at, going back to the section where I talked about imaging, maybe that can be a good motivating factor for people as well in terms of figuring out what the quality of their body tissue looks like in terms of the fat deposition and where they need to focus their energy on. Uncomfortable topic to talk about is environmental toxins. Persistent organic pollutants, bisphenol A, these are very well recognized toxins that can disrupt hormone signaling. They can interfere with the body's ability to use insulin properly, and I feel that we're just scratching the surface with this issue. I had a conversation with Professor Swan on the podcast recently, a couple of months ago, and it's kind of a scary conversation because there's a lot more knowledge about the impact of these endocrine disrupting chemicals on not just insulin resistance, but on fertility, on cancer. But simultaneously, there's not really much that we can do given how ubiquitous these chemicals are in our environment. And it's not just cookware and pans and plastic wrappers and food containers, all that kind of stuff. It's more the stuff that's in the air, the fumes that we breathe in, the fact that we live in cities, the fact that our waterways are polluted. So just a couple of notable studies that have explored this association. There have been a number of large studies looking at the association between environmental pollutants like POPs and nitrogen dioxide, particulate matter, which is something that I think is particularly an issue in urbanized environments, and the risk of insulin resistance and type 2 diabetes. There are clear associations between the more exposure to these chemicals and the likelihood of insulin resistance and type 2 diabetes and all the other metabolic downstream effects of IR, insulin resistance. The mechanisms underlying the associations that we see have also been quite clearly demonstrated as well. And these include things like impacting the insulin signaling pathway that we talked about earlier, hormone transport that we talked about earlier, impact on gene expression, the impact on receptor expression, there isn't much we can do about this. There's loads of information coming out now about the impact of these environmental pollutants and just how many different ones there are, and how, we're still yet to study a lot of the ones that are novel compounds that are being introduced into our commercial environments and home environments every year. And the only thing I really have to suggest is campaign for cleaner streets, electric vehicles, get more houseplants, be less wasteful, recycle plastic or try to use no plastic, change your pans. But I hasten to say all these different things that I'm suggesting don't really have evidence base around how effective they can be. I can't point to a significant study that shows if you clean up your home environment, you reduce your exposure to all these potential harmful effects of endocrine disrupting chemicals. So with that in mind, I'm continue to do that stuff, but it is under the cloud of not really understanding exactly what benefit they could be doing. They definitely make me feel better, but whether or not this is actually having an impact or not, I can't say. Definitely TBD on that. Definitely TBD. Sleep. Let's talk about sleep as a risk factor for cancer, weight, and yes, you guessed it, insulin resistance. Several studies have suggested an association between sleep deprivation and insulin resistance. There isn't a clear understanding of the mechanism though, and a lot of these studies, actually, when you dive into them, they have a wonderful headline. They have a wonderful, sleeping less than 2 hours increases your risk of diabetes by 4-fold. All these sort of like headline grabbing titles. But the actual studies themselves are really, really small. And so it's just something to bear in mind whenever you hear these sort of one-liners. A few notable examples of exactly this. In the Lancet, there was a paper called Impact of Sleep Debt on Metabolic and Endocrine Function. Great study. 11 healthy young men were the subjects used in this. So just 11, you've got to remember that. And the results, interesting results, however, the results showed that even short-term sleep restriction led to decreased glucose tolerance and insulin sensitivity, suggesting this connection between sleep loss and insulin resistance. Just 1 week of chronic sleep restriction, which is what these studies did, they reduced their glucose tolerance test to a level that was in line with diabetes risk. So to a pre-diabetic level, which is pretty phenomenal. If you think about just 1 week of poor sleep, I can remember, at least a couple of weeks in the last year where I've had really poor sleep. So it just goes to show that if there is this potential association, whether or not it's it's concrete or not, it's still a risk. And I'd rather lean on the side of pragmatically being safe. And there are a whole host of other benefits of improving sleep as well beyond insulin resistance, even if that's not a thing. Another study, 2009, 11 healthy volunteers reduced their sleep by about 2 hours on average. That led to an increase in snacking. And so although the meal intake remained similar, what they noticed was an increase in consumption from snacking that led to a higher amount of energy consumed in their typical 24-hour period. And from what we know about excess amounts of energy, particularly from snacks, that are also going to have the issues around being high salt, being high in processed items, being highly refined. These are all going to exacerbate insulin resistance, outside of the fact that the potential sleep mechanisms as well. Another one, 2016, this was published in Sleep Health. 15, again, just take note of the limited number of cohorts you had in these studies. 15 healthy, non-obese, young adults. They completed, this is quite interesting, they completed oral glucose tolerance tests. One was 3 days of time in bed restricted to around an hour to 2 hours less their average. And then they repeated that after having what they called ad libitum sleep, which is basically a science research term for as much sleep as you want. And what they found is that whilst the glucose and insulin concentrations, just the glucose concentrations weren't indicative of pre-diabetes or type 2 diabetes. They didn't see a massive significant difference in the oral glucose tolerance test, but the insulin concentration at fasting during the sleep deprivation stage was significantly higher. So this just goes to show what the whole theme that I hope you're cottoning onto during this podcast is: you might not have a positive or a red flag blood result, but there are things going on. There are mechanisms that are beautifully designed in your body to maintain that state or the appearance of normality on those blood results. Whereas in actual fact, in this study, as was eloquently described, your higher amounts of insulin are maintaining that normal level of glucose to the point where you become more and more resistant, and that's where you have the diagnosis of prediabetes or blood pressure or all the other things that we talked about earlier. So all these things suggest that sleep does have an impact. What could be going on? A number of things could be going on. So the short sleep duration could be impacting oxidative stress, so increasing the increasing reactive oxidative species that we know has an indirect effect on insulin signaling. It can impact your adrenaline, your cortisol levels, and the release of those catecholamines from your adrenals. It can activate inflammatory pathways. It can change adipokines. So these are the hormones involved in inflammation and hormone balance, increasing leptin and reducing adiponectin. All these collection of different pathways that can negatively impact your insulin sensitivity, these can coalesce in issues over time. So you can imagine a lot of the studies that we just talked about were short-term studies. If everything that they are pointing an association to is correct and using the mechanisms that they've postulated as to why that might be happening, a chronic sleep-deprived person is going to be having a lot of issues with insulin resistance, even if they do everything else right. Even if they eat generally well, they exercise, they can definitely mitigate it. But if sleep's a big issue, that's certainly something you want to double down. You want to dive into a bit more. So all those different things: appetite regulation, inflammation, increased sympathetic nervous system activity, catecholamines. These are all things that can compound into insulin resistance and leading to the metabolic disturbances. Okay. I hope, hopefully by this point I haven't completely scared you off the pod. We know why sugar balance is super important, what insulin is, how it does what it does, why we might become insulin resistant, the biology of insulin resistance, how we measure or how it's very hard to measure insulin resistance, how do we treat it? All right, let's talk about how we can potentially prevent insulin resistance or even treat it or manage it better. Aim of the game is to try and keep us insulin sensitive. That is to say, we want to be responsive to the hormone insulin without needing ever increasing doses of the same hormone to have the same desired effects. And the way we do that, one of the ways in which we do that, is to reduce the frequency and the size of glucose spikes that send signals to release insulin. So you want to lower the need for insulin. And there's various ways in which you can do that, ultimately to delay all the issues around insulin resistance that we've talked about at the start of the pod. I would love to talk about diet first, but the most effective mechanism, the most effective tool is likely to be exercise. Physical activity helps to increase energy expenditure and improve muscle insulin insensitivity, or improve sensitivity to insulin. We talked about why muscles and how muscles are the biggest store of glycogen. This is in part reason why exercise is so important, because it's not really about the physical activity per se, but more about muscle health. And to sum up the impact of exercise and improving one's muscle health, there was a lovely excerpt from a paper in Endocrinology from 2020 called Mitochondrial Dysfunction, Insulin Resistance and Potential Genetic Implications. I just want to read out this small segment for it. Multiple lines of evidence from human studies suggest the benefits of exercise mitigating insulin resistance and decreasing the risk of type 2 diabetes. Exercise interventions in healthy, insulin-resistant and diabetic humans have consistently, so both patients and healthy people, have consistently demonstrated improvements in insulin action, weight loss, ectopic fat distribution, that's fat where it shouldn't be, GLUT4 induction, so that's the protein responsible for glucose absorption in cells, phosphorylation of IRS1 and AKT, these are the proteins involved in signals of insulin, inflammatory profiles, mitochondrial biogenesis, so that's the production of new mitochondria, mitochondrial size, mitochondrial number, the oxidative activity of mitochondria, so they're doing their job effectively and they're utilizing fats instead of it being pumped into the cells, enzyme activity, ATP production. There isn't a single intervention that can do all of those things so effectively, and that's why exercise and improving one's muscle health through the action of exercise is the number one thing that I can suggest as improving one's insulin sensitivity and reducing the risk of type 2 diabetes and all the other metabolic complications. That isn't to say exercise is the only thing. That isn't to say that you can outrun a bad diet, although some people would suggest that you potentially could. But that's definitely not the way you want to approach things. You want to use exercise as a key tool. And if you eat well and you sleep well and your stress is low, exercise is just going to compound all those different benefits that you're going to be getting from all those different activities. So really, really think about exercise as a massive tool in the fight against insulin resistance. It's futile, I believe, to define a protocol of exercise that works specifically for insulin resistance. It's very hard to compare all the different studies, all the different subjects, whether they're obese, whether they have conditions, whether they're otherwise lean and healthy. I think it's completely futile. It's really about variety, regularity, and how you can fit an exercise regime into your day-to-day that doesn't interfere with your life and actually something that you can maintain. So I'll talk about the different types of exercise and the evidence for them, the general amounts that have been suggested as interventions for those different types of exercise, and give my sort of overall thoughts about how you can utilize that new knowledge and apply it to whatever regime. So first one, aerobic exercise, very, very well-known study published in the New England Journal of Medicine. The Diabetes Prevention Program found that moderate intensity aerobic exercise, so this is something like brisk walking, as simple as brisk walking, for at least 150 minutes per week. So split out, let's say 30 minutes times 5 days across the week, significantly reduce the risk of developing diabetes, which suggests that it can improve insulin sensitivity and glucose metabolism. A different study, Applied Physiology, a Journal of Applied Physiology, demonstrated that just a 12-week aerobic exercise program of 45 to 60 minutes of moderate intensity 5 times per week, so a lot more, improved insulin sensitivity in overweight and obese individuals. So look, there's a big range. The more you can do, the better. Great. There is obviously a caveat that you can overdo aerobic exercise, particularly if you're not maintaining your nutrition, you're not sleeping effectively. But look, we're all reasonable people here. If you can fit in a minimum of 30 minutes 5 times a week, that's absolutely wonderful. If you can only do 30 minutes 2 or 3 times a week, that's great. Any amount, any dose of exercise is going to be pushing you more towards insulin sensitivity, i.e. the opposite of insulin resistance. So whatever aerobic activity you can do, great. Is there a better one? Is running better than swimming, better than cycling? It's so hard to tell. My hunch would be that anything that better exercises the larger muscles, i.e. your legs, your thighs, your buttocks, is going to have a more demonstrable effect than your upper body, purely because of muscle size. You're probably going to get more bang for your buck, which is bringing me nicely on to resistance training. So another number of studies, the Journal of Medicine Science in Sports and Exercise, examined the effects of resistance training. They looked at resistance exercises twice a week for 16 weeks each session. It wasn't clear as exactly how many minutes they were doing for each session, but let's say 45 minutes per week, because that's what I've seen in other studies. 45 minutes per session, twice a week for 16 weeks. Again, improvements in insulin sensitivity and glucose disposal. The same sorts of exercises, resistance training, 3 times a week for 22 weeks. A different study in the Journal of Diabetes Care investigated that exercise regime, and that study showed significant improvements in insulin sensitivity as well. So whatever you can do from a resistance exercise point of view every single week, fantastic. It does not need to be going to the gym and lifting heavy weights. It can be a case of body weight exercises, squats, the types of exercises where you contract your muscles against resistance for a long period of time. That can use bands, that can use bars that you pull against or push against. Those are things that would be wonderful for resistance exercises. I think a lot of people incorrectly assume that you always have to be lifting heavy weights for resistance exercises. Pushing, pulling, sleds, for example, anything against friction that you can do to move your leg muscles in particular would be wonderful. So resistance training, absolute tick. And then, of course, you've got the more popular cousin of all these different types of exercises, which is having a moment, which is HIIT training or high intensity interval training. This is where you go there's various modes of HIIT training. There's Tabata, there's 4 minutes on, 4 minutes off. There's other sort of modes where it's like as many reps as you can do within a defined couple of minutes, and then you have a short break and then you go again. It's very hard to compare all these different exercise modalities against each other, because depending on the person, depending on their motivations, depending on their ability to consistently work out in that way, that's where the benefits are going to accrue. A one-off session or a period of, say, 12 weeks, like in these studies, where they were able to do these exercises in a confined clinical environment where they're motivated and they have all the skills and coaches to push them through it, even if it yielded better results than one type of HIIT training over another, it doesn't necessarily matter, because in the real world, it really depends on what you prefer doing, what you can do, what's convenient for you, what you like doing as well. So those are the things that I would suggest you really focus on, rather than I need to do this specific type of high intensity interval training. A simple training technique that I use is sprinting for 45 to 60 seconds, either on a treadmill or outside, preferably outside, because you're getting the double dose of the outside air, vitamin D, sunlight, exposure to nature, all those wonderful things. And then taking a break for 30 to 45 seconds and then going again. You want to try and keep that break in between sets as low as possible. And doing that for 15 minutes is... it will really push you. And if it doesn't push you, you're not going hard enough during the sprints. You should feel terrible during the activity. Afterwards, you feel great. Obviously, make sure that you're not pushing your limits, because that will obviously lead to negative outcomes. So do this within reason. You want to have the smorgasbord of all those different types of exercise. So bit of aerobic, bit of high intensity interval training, and a bit of resistance training. The perfect board, let's say, I don't believe there is a perfect board, but let's say you wanted to know exactly what you should be doing across the entire week. Well, it seems as if at least 150 minutes of aerobic exercise, so jumping on the bike, running, rowing, split across 5 different sessions. If you can push to 45 minutes or even 60 minutes, great, as long as you're ensuring that your nutrition is going to be balancing the energy expenditure that's required of such intense activity, coupled with, so that on top of at least 3 HIIT sessions per week, on top of 2 resistance sessions per week as well. I think that from the perspective of insulin resistance is fantastic. People go to the gym for different reasons. People go to the gym for heart health, for metabolic health, for aesthetics. People want to look good naked. And depending on what your goals are, your exercise regime is also going to be shaped by that. So I don't want to suggest that, all right, to be insulin sensitive, you need to do all these exercises and that's it. You have to weigh up exactly what your goals are as well. My goals, speaking quite frankly, is going to be a mixture of, yes, maintaining metabolic health, yes, maintaining lean muscle mass, but also aesthetics, quite frankly, as well. So I don't want to look too skinny. I don't want to look too big. I want to have a reasonable build that makes me feel confident in my day-to-day. And that's the reality of exercise regimes for a lot of people, whether you care to admit it to yourself or not. A lot of people have that in the back of their mind when they're at the gym or exercising for whatever reason. So that's exercise, the most powerful tool. If that's the only thing you do, great. If you want to take it a little bit further, let's go into diet. So I really don't like talking about headlines and dietary studies that much anymore, but just because there's just so much conflicting evidence, I would much rather do a deep dive into particular ingredients and look at how wonderful they are and how diverse they are than trying to figure out the exact macronutrient proportions that align best with a goal like insulin resistance. Because in reality, it's so hard to actually determine the clear signals from the noise of nutrition science. When you hear the words high sugar, how do we define sugar? How high is high? When you hear the word carbs, what carbs are we talking about? Are we talking about carrots and parsnips that are all carbs? Or are we talking about sugar, table sugar, or white rice that are all carbs? When we talk about high fat, how high is high? What kind of fats are we talking about? What proportion of the plate is being displaced by that high fats? Like how many? If we're having high fat, that ultimately means something else needs to be lower. And what is that? That's lower. So all these different headlines that I find very, very hard to separate the wheat from the chaff. I'll give you a few examples. So Journal of Clinical Endocrinology and Metabolism 2019, a study found that high-fat diet increased insulin resistance by impairing insulin signaling in skeletal muscles. That's the headline. How do we figure out what types of fats were in said diet? How was that standardized? If it was based on a food frequency questionnaire, how did we determine that people knew exactly what a fat was? Most people incorrectly assume that a burger is high fat. It definitely has fats in. It definitely might not have the right types of fats in, but it's also got a lot of refined carbohydrates in. So how do you separate all that stuff from those kind of questionnaires? But let's just say high fat diet, not having too many fats is going to be bad for insulin resistance. Another study published in the Journal of Nutrition 2017 examining the effects of adding high sugars to a diet. So they obviously concluded that a high sugar diet led to increased insulin resistance by promoting inflammation and oxidative stress, etc., probably by spiking insulin and leading to intolerances because of the promotion of insulin in the bloodstream. So all these different elements are definitely going to have an impact on your overall risk of insulin resistance. So high sugar's out as well. A study published in the Journal of American Medical Association 2005, this study showed that low-fat, high-carb diet improved insulin sensitivity. One of the mechanisms that they proposed was increasing insulin signaling in liver cells. How high is high carbohydrate? What kind of carbohydrates are we talking about? How low is low-fat? What fats were removed? Were were products that are labeled low fat, i.e. they have the fat stripped out of them and they're usually replaced by either fillers or in some cases sugar. Were those the types of ingredients that were used? There's so much nuance to nutrition science that it's very, very hard to look at a specific macronutrient determined diet and make the suggestion that this is the type of diet that one should be following, particularly as we all have very nuanced responses to different diets. We were talking about genetic implications for insulin resistance. That will determine how bad an egg is for you consuming it versus me consuming it. Eggs generally quite healthy, but yes, they contain dietary cholesterol, and yes, they contain saturated fats. One's ability to absorb that dietary cholesterol and excrete the majority of it, which is the case in most cholesterol-containing foods, including animal products, that's most likely the fate of taking in a high cholesterol item. But some people will absorb a little bit more of that. There is a general figure of 15% of the cholesterol that is absorbed out of a high cholesterol containing food. So it's thought of as a minimal amount. But there is a variation in one's absorption of that cholesterol. 15% might be the average. How much is it at the top end? How much is it at the low end? And how do we determine individual variability between one's absorption of those different types of fats? There is so much unknown, and so I think it really boils down to finding a consistent pattern of healthy eating that works for you. And so from my perspective, a high fiber, varied, plant-focused diet is the most pragmatic way to start a diet or a way of eating rather than the diet. Essentially, the nutrition interventions that work for insulin resistance, as dictated by the mechanistic studies, are calorie reduction. So what happens when you're on a low calorie diet, and I'm not promoting a low calorie diet here, I'm just saying it as how it is, but what happens on a low calorie diet is that it reduces something called acetyl-CoA and improves insulin resistance via the liver. A low calorie diet is not something I suggest because it's very hard to maintain over the long term. It 100% will reduce your weight in the short term. But what happens as we live in such a complex foodscape, it's very hard to maintain that low calorie way of eating over that period of time when you've lost weight. If you were to return to the same energy consumption at the start of your low calorie diet, you tend to put on more weight. And the reason why is because during the low calorie diet, your weight set point changes. And when you reintroduce even the same amount of energy after that low calorie diet, your body will absorb more, it will hold on to more via various mechanisms that involve insulin, as well as a whole bunch of other hormones as well. So really important to make sure you caveat if you are going to go on a low calorie diet. And there are lots of options, I believe, today in a therapeutic manner to improve insulin resistance that are marketed at people who might be pre-diabetic or even diabetic. So things like very low calorie diets, fasting diets, traditional weight loss, calorie restricted diet plans. They are effective short term. I would suggest, or I would postulate that it only helps the minimal amount of people, not the majority of people, because the majority of people, unfortunately, yo-yo dieters, and they tend to put on more weight over time. So that's my 2 cents on low calorie diets, but it does appear to improve one's sensitivity to insulin, at least in the short term. The other thing is the avoidance of carbohydrates that stimulate excessive insulin demand. What carbohydrates are those? Refined carbohydrates. So things like pastas and biscuits and chocolates and bars and a lot of the healthier for you items that are labeled as such that are actually quite high in sugar and refined carbohydrates, and that will spike your insulin demand. So those are the things that you want to try and avoid, and instead introduce more whole grains, more fiber, and the items that I'm going to talk about in a second when we talk about the gut. that's all I'm going to say about overall dietary patterns. I think it's quite a difficult subject to boil down to very, very simple takeaways. But maintaining a healthy way of eating combined with exercise is going to be the best strategy. Third thing, another thing I really don't like talking about is saturated fats or carbohydrates, for that matter, in one sentence, because it lacks nuance. And in reality, there are many different types of saturated fats that come in: short, medium, long chains. You'll see lots of different headlines like diets that are high in long chain saturated fatty acids are associated with decreased insulin sensitivity and increased risk of diabetes type 2. And on the other hand, I've come across headlines that say, okay, medium chain saturated fatty acids that are found in coconut oil have actually been shown to improve insulin sensitivity. Again, with the same caveats that I talked about above, it really lacks nuance. And I think the thing about nutrition is that the environment in which you live, the quality of the rest of your diet, and how well you are able to maintain that way of eating are huge determinants of your overall the overall preventative power of that diet. So I don't think it's worth going through saturated fats in much detail. What I would say is that the likelihood is saturated fats that come in all sorts of products, including oils, animal products, nuts and seeds, can be healthy depending on the wholesome nature of the unprocessed nature of the ingredient. So nuts and seeds, I'm a big fan of, and they, yes, contain saturated fats, some more than others. So almonds, for example, in 100 grams will contain 3.7 grams of saturated fat. A higher saturated fat containing nut is Brazil nuts. They contain 15 grams of saturated fat. Does that make Brazil nuts worse than almonds because of the saturated fat content? No, not necessarily, because within Brazil nuts, you have vitamin E, you've got magnesium, you've got zinc, you've got all these other polyphenols, you have these other fatty acids that are actually anti-inflammatory. There's so much to this wholesome ingredient that actually has a number of other constituents that provide health and promote health, that ultimately you lose the holistic picture if you just focus on one nutrient at a time. And this nutrient by nutrient science, I think, clouds the whole picture of one's eating habits that can promote health. So again, that's my 2 cents on saturated fats. I would not read into it. I would really focus on getting wholesome sources of saturated fats or fats in general. Quality fats are one of my principles of healthy eating. Nuts, seeds, quality extra virgin olive oil is my go-to. Olive oil, although I do have coconut oil and sesame oil in varying amounts depending on the cuisine that I'm cooking for, and in moderate amounts as well. So I'm not pouring in lots of oils, and I'm not eating, or I could eat bags and bags of nuts, but I'm not eating bags and bags of nuts because I want to vary out my diet and eat a variety of different items as well. So that's exercise, biggest tool. Diet, something to get right. Don't eat too much. Eat wholesomely. Saturated fats, I'm not concerned about. I think the titles around high saturated fat diets can be conflated with high processed diets, highly processed diets, and I think it's very hard to disentangle the two. The gut, our good friend, the gut. This is going to be, I think, a really interesting area of future research that could determine one's likelihood of insulin resistance, because there's so much to unpack and there's so much that we don't know. So rather than the sort of simplistic perspective of out with the bad bugs and in with the good, it's more a case of rebalancing. So bacteria can improve insulin sensitivity by generating short-chain fatty acids. These are things that we've talked about before. And the way in which they generate these short-chain fatty acids is through fermentation of dietary fiber. So the more fiber and the more variety of different fibers you introduce into your gut, the more likely that they are going to be creating all these different sorts of SCFAs. These are short-chain fatty acids The key ones that are always mentioned in academic papers are butyrate, acetate, and propionate. And they're important because they're energy sources for cells lining the gut, and they've been shown to have anti-inflammatory effects locally. And specifically, butyrate has been shown to reduce inflammation in several ways, inhibiting the production of pro-inflammatory cytokines that we mentioned earlier, like IL-6, TNF-alpha, and also produce and enhance the production of anti-inflammatory cytokines as well. So in an indirect way, because if you remember, inflammation is indirectly associated with insulin resistance, in an indirect way, your gut microbes, the ones that produce all those different short-chain fatty acids, can improve insulin resistance. In addition, short-chain fatty acids can also improve insulin sensitivity by promoting the production of something called incretins. Incretins are hormones that stimulate the release of insulin from the pancreas in response to food intake. They also do this on gut endocrine cells that stimulate the production of these incretins and promote proper insulin secretion. So that's there's a number of ways in which your gut microbes that produce short-chain fatty acids that overall have a net anti-inflammatory effect can influence insulin resistance. Another way is by, like I said at the start, rebalancing the different microbes. So overall, bacteria that come from the genus Lactobacilli are thought as the good guys, quote unquote. And then you have others like Firmicutes and Bacteroides that are from a different type of class, a different type of phyla. Those are universally thought as the bad guys. I think in reality, the more we find out about these different types of bacteria and microbes, we're going to realize that they all have their roles, and it's not a case of ridding ourselves of one complete type of species. It's more a case of rebalancing and ensuring that we have an environment that allows the right ones to thrive more so, to create balance in our metabolic health, our mental health, and all the other impacts that our gut health has on our body. Lipopolysaccharides, these are probably things that you might have come across. It's sort of making its way into marketing material for a lot of gut health products. LPS, as is also known, lipopolysaccharides, LPS, is the component of the outer membrane of gram-negative bacteria. So the bad guys, as they're normally suggested to be, even though I think that's a misnomer, that contains Firmicutes and Bacteroides. When these bacteria die, they have these LPS on their coats, essentially. They're on the outer shells of these gram-negative bacteria. And when they die, this LPS can be absorbed into the bloodstream. When it's in the bloodstream, this LPS can trigger an immune response that generates inflammation. This LPS shouldn't be in the bloodstream. Your immune system is alerted to it. It triggers an inflammatory response, which is a genuine response in it, and it's appropriate. And that promotion of inflammation can impair insulin signaling in target tissues such as the liver, the muscle, and adipose tissue as well. So just that fact should trigger in your brain now all the sort of downstream effects that can happen from excess inflammation. In addition, there is a suggestion that LPS directly, so that's an indirect mechanism by which it can impact insulin resistance. There is a direct mechanism by which LPS can impair insulin resistance or impair insulin signaling, and that's by activating something called TLR4 or toll-like receptor 4. You don't really need to know about the names and the nomenclature of everything, but activation of this TLR4 can trigger a signaling cascade that impairs insulin signaling and promotes insulin resistance. So overall, promoting a healthy microbiota where you have a good balance of all the different types of species and the different types of microbes will lead to better insulin sensitivity and overall lower risk of metabolic disease. How do we look after our guts? You've heard me talk about it many, many times in the podcast before. It's high fiber. It's a variety of different types of largely plants. It is prebiotics. These are specialized types of fibers like garlic, chicory, artichoke that are uniquely positioned to promote the variety of microbes that we want to have. Probiotics may have a role, although it's so hard to determine from all the research about which specific strains of probiotics are appropriate for which person. But a general probiotic with lactobacilli, or preferably something that you can get from yogurts, ferments, kimchi, wonderful. Other things that would promote better gut health, stress, exercise, our good old friend exercise, and happiness states. It's hard for me to prescribe an anti-stressing pill or a pro-happiness pill, but there are definitely things that you can do within your lifestyle to mitigate against stress, improve happiness, and exercise that will definitely improve your gut microbiota and lead to better metabolic health as well. The other thing, so we've talked about these interventions. So we've got exercise is number one, most likely. We've got diet. We've got improving the microbiota. The other things that I'm not going to spend too much time on because it's just very hard for me to prescribe are removing pollutants because of the proposed potential issues with those toxins on endocrine disruption. The two other big ones are stress and sleep. So doing stress relieving activities, whether that be walks in the park or meditation, mindfulness activities, those are definitely elements that can improve one's insulin sensitivity. And the other thing is sleep. So sleep is a really important factor in insulin sensitivity and maintaining metabolic health, but it's very hard for me to practice it myself and very hard for me to prescribe as well. So rather than going on about all the 10 different things you can do to improve one's sleep, you've probably already heard it before. I should do another podcast on it to determine exactly which protocols for sleep are beneficial or have the biggest weight of evidence. CBT is, I would say, the gold standard for improving sleep. But there are other hacks and things that I can talk about in another episode on sleep where that could have a marked effect on insulin sensitivity as well. And that's it. So look, today we've talked about a lot of things. We've talked about the impact of pollutants, exercise, diet. We know a lot more about metabolic health, what that means, why insulin is so important to sugar regulation, the biology of insulin resistance, what the causes of that insulin resistance could be, how to mitigate it using the biggest tools that you have at your disposal, exercise, diet, and all the other things that we talked about with regard to improving microbiota health, sleep, removing pollutants, and stress. Next time, we're going to be talking about the sort of hacky things that I didn't really want to talk about on this episode because I think that can detract from the real big tools that we have. If you focus on the big tools, the hacks and the supplements, those are nice to haves, but they're not the mainstay of treatment. I would say let's focus on the big tools. And then we'll also be talking about a little bit about supplements and the drugs that are available for insulin resistance as well in a little bit of detail. I hope you enjoyed listening to that. I'm going to be doing a few more of these solo episodes. So if you do want me to do a deep dive into another subject, whatever that might be, leave a comment on Twitter or YouTube, or sign up to the Eat, Listen, Read newsletter. And we always have a feedback form there that we always dive into, and we look for any themes. So I'll look forward to seeing you there.